Hey, welcome everybody. My name is Rob Payton. I'm a hydrologist in the Department of Land Resources and Environmental Sciences. Most faces are familiar, but a few aren't. So if you don't know me, that's who I am. It's my honor to be invited to introduce Dr. Payton Gardner to give a talk here at Montana State from the University of Montana. Payton has his undergraduate bachelor's degree from the University of Montana. And has a master's and PhD in geophysics from the University of Utah. He spent 2 years at a postdoc in CSIRO in Australia, I presume it was in Australia?
It was in Australia.
And then worked for the Sandia National Lab for a few years. Over that time, he was invited to be an expert consultant with the International Atomic Energy Agency. And I'd like to hear some stories about that. I imagine that has something to do with safe storage of nuclear waste in the subsurface.
Yes.
And back in 2015, Payton came back to Montana to be an assistant professor at the university. And I am immensely entertained every time I hear from Payton or Kelsey Genso from the University of Montana about this argument that keeps going back and forth about soil processes and groundwater processes. And a little jealous I don't get to take more active role in those arguments. So I think this talk is going to be a little bit about that, and I'm excited to hear more about it. So please welcome Payton.
Well, thank you, and thank you for inviting me and coming to my talk. Rob, you need to come out with Kelsey and I, because I've been beaten up on the soil hydrologists lately, and they need some help. No, I'm just kidding. He usually wins. All right. So today I want to start talking or introduce you guys a bit to the role of deep groundwater and bedrock groundwater in mountains and mountain block recharge. It's probably an area that not a lot of you are real familiar with, and that's because not a lot of us are real familiar with it. So if I figure out how to advance the slides. All right, there we go. So I'm starting my third year of being a professor, and I'm finally getting to the point where I'm starting to steal results from students. So it's with great pride that I get to acknowledge students that I have blatantly stole their work from. All right, my lab is starting to work for me. All right, I'm not sure it's an easier way to do things, but it is a good way to do things. So I'd like to thank my students, Isabella and Derek and Kim. I work a lot with Kelsey Genso's lab up in forestry, and Rob and Zach are his grad students. Rob's kind of a co-grad student between us, and they've been really helpful in this whole project. And then Kelsey and Marco, the Watershed hydrologists at U of M, it's been an amazing experience to spar academically with them and to try and meld our two visions of how hydrology works. So I'd like to start off with this. This is a map from the Groundwater Atlas showing water resources in western Montana. And the known water resources are these yellow, in western Montana, around Missoula, the known groundwater resources are these yellow patches here. All right. These are all alluvial aquifers in the basins right around the river. They're very confined in extent, and they're very small. And I'm taking over for a very illustrious groundwater scientist. And if I was to go up here and say I want to do a study in the, say, Bitterroot Valley, well, Bill Wussner, who I'm taking over from, has done at least 3 or 4 studies in the Bitterroot Valley, and I got to get really creative to do something new. But what I want to focus on is this gray area, the area out here outside these very confined areas, and try to understand a bit more about the groundwater hydrology of mountain systems, all right? And in the area of groundwater, I would say this is definitely still a gray area, all right? We don't know a whole lot about how groundwater systems move in mountains and how they work. So this picture was taken on the Nayak Floodplain, and here I'm being a good groundwater hydrologist, and I'm drilling holes down in the floodplain right next to the river. It's easy access. but I'm peering up here at this dark mass, all right? And I'm wondering, what does the groundwater system look like up there? It's really easy for me to poke holes in here and understand how groundwater moves in the alluvial aquifer, all right? We have very few groundwater wells up high. We don't know a lot about whether there's groundwater flow up there, how much it is, how much it contributes to the lower aquifers down here. And really, if you want to understand the groundwater system down low, you need to know something about the boundaries. How much water is coming in from the sides? Is this a mountain of groundwater? Is it just a big block of rock? All right, what is this? So today I'm going to try and illuminate a little bit about what's going on up here in the mountain block. So a lot of this talk focuses on some discussions that are going on in the literature right now, in the hydrologic literature, but are also exemplified when I go out with Kelsey's group or with Marco's group about how we look at the world and the hydrologic world. All right, so it boils down to two different cartoons, and that is that mountain block a Teflon surface and all the water moves through this thin layer of soil across the top, all right? Or, this is the sort of traditional watershed hydrologist view, or is it the traditional groundwater hydrologist view where the whole world's just a sandbox and everything moves down until it hits the water table and then it moves to the river, all right? So what I want to do is try and meld these two visions, think about how they interact and how important each process is. So the very first question we need to decide is, why do we care about deep groundwater? It is the least investigated portion of the hydrologic cycle by far. Paul Stoy was telling me earlier how hard it is to measure soil moisture, and I almost started laughing because I was like, well, I'm trying to measure fractured flow in deep mountain blocks, and let me tell you, I think soil moisture is really easy to measure. It is really hard to get at. So why do we, and it may or may not be important. We don't even know enough about it to really know that. Now there is a lot of literature saying it is important lately, but we don't know a lot about it. So why should we even care? So I want to consider a sort of hypothetical watershed right after we've had some precipitation. The groundwater tables are full, the soil water table is full, and we have a lot of different water discharging to the river, all right? We've got sort of short, local, shallow flow paths, say through the soil, and then we have some deeper flow paths that are probably moving through the bedrock, all right? So we've got everything contributing, we're happy, we're full of water, and then it stops snowing or it stops raining. In Montana, we hit June, all right? And we stop losing all our precipitation. The first thing that we lose, the first thing that drains out are the shorter, shallow flow paths. And as we go a longer and longer time, since the last rain event or last precipitation event, it is the deepest, oldest groundwater flow paths that provide the buffering capacity for our watershed, all right? So I went to a social science talk yesterday, and they talked a lot about the term resilience, right? And it's a new buzzword, both in ecology and in social science. Well, you can think of the groundwater system as a major component of the resilience of your watershed, all right? It allows the watershed to buffer these big changes in precipitation input, all right? And it gives some amount of contribution to the watershed, even in times of long drought, all right? So this is your buffering capacity. And that as our precipitation patterns change, as we see greater fluctuations in precipitation, it's gonna be these resilience factors in our watershed that are gonna allow our watersheds to behave at least somewhat similarly under changing climatic conditions. So the first question So the second question, I'm going to argue that it's important we understand this. So the second question is, well, is it real? Does it exist? All right, so to start answering that question, I'm going to move out of the theoretical realm a little bit here, and I'm going to move up into the Cap Wallace drainage, which is in the Lubrecht experimental forest north of Missoula. All right, and this is a drainage that drains to this single Cap Wallace Creek. And here we've been instrumenting this watershed to understand a bit more about soil water, groundwater, and stream flow generation. These triangles here are stilling wells in the stream where we've collected discharge measurements throughout the spring, summer, and fall. All right. We've also collected chemistry, water chemistry at all of these sites. We have done synoptic measurements of stream chemistry at multiple periods throughout the year. These orange dots here are shallow soil wells, where we've pounded in shallow soil wells to the bedrock interface. All right, and they are there to sample that shallow soil flow above the bedrock. And then these squares here represent a lot of blood, sweat, and tears where we actually got a drill up on the hill slope, all right, and drilled holes to 10 meters depth roughly below the soil zone into the intact bedrock, and they're sealed off to the soil. So these wells only measure the water level in the fractured bedrock beneath the soil zone. So let's focus in on these bedrock wells and look at the hydrographs, or the hydraulic response from these wells. So this is the hydraulic response from the upmost well. So this is the highest well in the landscape. I want to point out a few things. All these wells are not down in the bottom near the stream. They're actually quite a ways up on the hill slope, not too far from the drainage divide. So we're quite a ways up the hill slope. All right, we're not near the stream. And this is the water level. So we put the well in this summer. It was dry, or we put it in last summer. The well was dry. All right, and starting March of this year, we see a big jump in water level. All right, you get 3 meters of jump in water level, coincident with spring melt, snow melt. All right, we have about 3 meters in the well until May, when most of the snow had melted off, drops back down. We had a really big rain event in June of that year, about 3 inches of water up in Lubrecht, which is a lot for us. Saw another big spike in water level, another 3 meter rise. And then in late June, early July, we got another big rain event, and we see another big spike in water level, right? So this groundwater well is showing dynamic 3 meter responses in the bedrock system, all right? So we're getting big responses, seasonal responses in the groundwater system. And this well is up high on the ridge, basically. Now I'm gonna move to another well, a little farther down in a hollow. We installed this well. This well has had water in it all season. It hasn't gone dry yet. During spring melt, we see another about a 2 meter rise, a bit more muted rise here. It comes down, we see the response of these two big rain events, and then it comes back down to its sort of long-term average water level, all right? And here I'm gonna move to another well that is sort of at the same elevation, but on a divergent landscape. And here we have a dry well after installation and through the winter. And then during spring melt, I see a 5 meter jump in water level, all right? So this is a big water level rise. It stays high over most of the summer, and then starts to decline, right? So the point here is that these groundwater wells way up high, far above the far above the stream and well below the soil zone are showing very dynamic responses, seasonal responses. This is an active groundwater system. It's seeing really big responses throughout the year, all right? So I want to move from, in hydrology, we sort of have three techniques, or in watershed hydrologists have sort of three techniques to investigate the system. One is these hydraulic responses, just looking at where there's water, how long there is water, looking at hydraulic connections. The next is physical modeling, all right? So I like physics, and I like physics-based modeling, and so what we're going to do is try and look at some numerical investigations of the mountain block itself, all right? And to do that, we're going to simplify the mountain block to a sloping slab, all right? The difference in my sloping slab from the sloping slab that most others have done is that we're going to consider a full 100-meter depth of bedrock, and overlying it, there's 2 meters of soil, all right? And I'm going to say that at the base of this slope, there's a seepage boundary condition, like the river, simulating the river. At the top, I'm going to apply a flux. All right, I'm going to do both transient and steady state fluxes. We'll look at the difference between those two. Simulating precipitation at the top. And what we're going to look at is the long-term or the distribution of saturation and groundwater flow paths, both in the shallow soil and in the deep groundwater. All right, here's some equations. I don't want to get into the details here, but on this block, I'm going to solve the full Richards flow equation across the entire block, all right? Richards equation is the proper physics for variably saturated fluid flow in the subsurface, all right? By solving full Richards across the entire mountain block, I'm not taking the typical shortcut of a watershed hydrologist who treats it, who uses a simplification of Richards equation and uses a kinematic wave equation for flow in the soil, all right? I'm also not taking the usual shortcut of a groundwater hydrologist who assumes saturated conditions and uses the fully saturated Darcy equation, all right? So no shortcuts, all Richards equation. The problem, the reason why this isn't done is it's really nonlinear, numerically very intense, all right? So we have to use a code that's high performance, scalable to many processors. All right, so I don't want to get into the details of the code, but it's a really computer science in this code's amazing. It really scales well to multiple processors, so we can solve this simulation in a reasonable amount of time. And what I want to do is first look at a reference case result. All right, so this is a steady state. What I said is there's some fictitious amount of precipitation falling constantly equal to close to the average precipitation of my site at Lubrecht, all right? And it's just constantly falling across the top. And what we see here is the steady state equilibrium distribution of liquid saturation. So my block here is now colored by the liquid saturation. So these blue areas are areas where the mountain block is fully saturated with water. All right. And these lines here are flow paths that originate in the very top layer of bedrock. All right. So these are flow paths that originate in the very top, and they are colored by the transit time, or the length of time it takes for a particle to move through this system, given the fluid velocity. So down here, they're a little more red. It means the water's old. All right. Okay, so there's a couple things I want to point out here. First of all, the mountain block is saturated up to a point, all right? So there is a groundwater system beneath here. Oh, I should also state that I've taken porosity, hydraulic conductivity, and capillary pressure functions. I've parameterized this model with very reasonable numbers for fractured bedrock in the bottom part of the model, and up top for the soil measurements that we've measured at Lubrecht. All right. So there's three main things I want to point out here. One is that there's a big unsaturated wedge, all right, above the water table in the mountain block. The soil zone above this unsaturated wedge is more saturated, all right, there's more water. There is a zone right here where there's actually a groundwater ridge. This is a zone where groundwater is being recharged into the deep bedrock groundwater system. And as we move downstream, or sorry, down slope, groundwater is discharging to the soil zone. And where I have continually saturated water in my soil, I have groundwater discharge. All right, so groundwater discharge is augmenting my soil moisture down low in the slope. So let me look at this in another way, and that is, first let's look at the saturation, the soil saturation. So on this plot, I've plotted the saturation level of water in the soil just above the bedrock versus the flux or the fluid velocity in the bedrock just below the soil zone, all right? And the soil is least saturated the farther upslope you go. So this dot right here is starting at the top of the hill, and it is the least saturated soil, all right? And as we move down slope, my saturation in my soil gets bigger and bigger and larger, so I have more and more water in the soil zone, all right? This is all looking good. But I have, high up on the hill, I have no fluid velocity in the bedrock. There's no water entering the bedrock at this point. All right, I reach a magic number of soil saturation of about 75%, and all of a sudden water starts to be able to move down into the bedrock, all right? So as Rob corrected me, I have reached field capacity at this point, all right? And gravity is able to drive my water down into the bedrock system and not laterally along parallel with the slope, all right? And that only happens when I have enough moisture in the soil zone, all right? I have a peak recharge at a soil saturation level of about 90%, all right? And then I start to actually reduce the amount of recharge, and when this number goes above 0 here, I actually have fluid velocity leaving the bedrock and into the soil. So what this plot says is that in areas where I have fully saturated soil, those are actually groundwater discharge zones. So in areas on the landscape where we go out and we measure continually saturated soil on the hill slope, those are actually groundwater discharge zones. We can look at this in another way. Here is distance down, this is distance upslope, all right? And this is either the saturation level or the amount of recharge, the volume of recharge. All right, so this blue line is just the soil saturation, or these blue dots. And what you see is that soil saturation increases as I move down slope. All right, looks very, very smooth and uniform, and it increases until I get to about 75 meters down slope. Then I'm fully saturated the entire time. This is the saturation in the bedrock, but immediately beneath the soil. And this stays very low it doesn't start to increase until I reach that magical 75% soil saturation, and then I start moving water into my bedrock system, and the bedrock saturation starts to increase. All right. I have this threshold behavior here where I cross from the dominantly recharged to starting to move soil water to or bedrock water to the soil water. All right. And where I cross the zero line here, this is the fluid velocity, where that crosses the zero line, and now water is entering from the bedrock into the soil. My soil rapidly saturates, all right? And my bedrock and soil stay saturated to the toe of the slope. So the take-home messages here are two. One is that initiation of bedrock groundwater is dependent upon the soil saturation state, and it shows a very threshold-like behavior. It doesn't occur until we reach field capacity, and that is at some location downslope. We have to have accumulated enough moisture from the upslope soil flow until we will initiate recharge. All right. Recharge occurs over a certain area of the slope, and the bottom of the slope is actually a groundwater discharge zone. So in the bottom of the slope, groundwater is augmenting soil flow and keeping the soil saturated. All right, so this is my sort of standard steady state analysis of this fictitious block where I've kept a very constant rain, all right? And there's a real question whether that holds any water or any realm of truth in an actual variable precipitation case where we're constantly getting precip in different amounts and different durations. So to investigate that, I'm going to present some results on transient recharge on the Cap Wallace watershed. So here is I've taken the SNOTEL data. We have at Lubrecht, we're lucky we have 2 SNOTEL sites, all right? And so I have 50 years of SNOTEL data. I'm gonna take the last 10 years of SNOTEL data, and I produced at least a reasonable infiltration rate or recharge rate to the soil zone from that SNOTEL data. This orange, I basically look at the precipitation amount or the snow water equivalent loss during the winter, all right, or during spring snowmelt. I let some of that be lost to overland flow or through-pack snowmelt. And then I let some of that be lost to evapotranspiration, which is calculated from a thorn weight calculation. And the result is my infiltration. So the actual infiltration is this orange line down here. Us hydrologists could argue about whether this is the exact right infiltration equation. It's probably not, but it is reasonable. All right, it's giving the right magnitude of snowmelt infiltration during spring and addition from precipitation later in the year. All right, and it's reasonable. All right, so it's at least a reasonable approximation to the probable recharge or seasonal recharge on the mountain block. All right, so here's the results. We're going to watch a little movie here of the transient saturation. All right, it's the same block. We're going to see the same flow lines. And there's 2 things I want to point out here. One is this time. This is going to be 10 years of simulation. And this time starts 0 time. This is a water year simulation. So it begins in October. So the main thing there is when this decimal over here is 0.6, that's spring and it's snow melt. All right. And the rest of the year, it's pretty much dry. Okay, so I'm going to start the simulation. So again, here's the flow paths. I'm basically outputting a step every second here or every day. So what I want you to see is that this groundwater recharge ridge is going to move up during the spring and come back down. So here we've got spring, we get a saturation event. All right, I see water coming in, it's moving up slope. My groundwater ridge is moving up slope. All right. The other thing that's really cool that happens during the spring is I get this nested short groundwater flow path that's transient. It only occurs during the spring, and this area that is normally groundwater discharge flips for a very short time and becomes a groundwater recharge and a nested flow path. So there's this ephemeral short groundwater flow path at the toe of the slope, and there's this long-term slow groundwater recharge point at the, about 2/3 of the way up the slope. And this recharge zone moves up and down throughout the year as it soaks up the spring snowmelt and then drains back down to the toe of the slope through the summer. All right. So I like to think about this as a big shock absorber. All right. My groundwater ridge is moving up, filling storage up in the mountain block, and then during the long summer afterwards, it's draining and it's subsidizing the soil moisture down at the bottom of the slope. All right. So there's two things here. The soil is still the main conduit. The water is moving through the soil, but a lot of it is taking an excursion into the bedrock. Some of it is entering at this point up here 2/3 of the way, and some of it enters in that nested, ephemeral, short groundwater flow path during the spring. All right. So let's look at some of these transient recharge dynamics. So this is my upslope saturation length on this x-axis, and these blue lines. This top one is the saturated length. This is the length upslope that my bedrock is saturated. All right. So here we see that, and then my green line here is the discharge out of my hill slope. All right. So during spring, you see a kick up and discharge from the bottom of the hill slope. That is when that is happening. We have snowmelt occurring, and when that happens, my groundwater level, or the head in my groundwater system, is rising upslope. I saturate the groundwater system farther and farther upslope. All right. And then through the subsequent summer, I slowly drain my bedrock down as I drain the bedrock out. All right. So this bedrock system is seeing large seasonal changes. All right. It's a very dynamic system. It's basically moving up and down throughout the year. All right. This bottom line is the soil saturation length. All right. And it's doing the same thing. And this has been shown by multiple people. Kelsey has shown this among others, that as spring happens, you saturate your soil upslope, and then those saturation levels drain down as the summer continues. All right. So the soil is doing the same thing as the bedrock, but I have another take-home message here, and that is that the soil saturation upslope length is always shorter than the bedrock saturation upslope length. So if I measure saturated soil, usually I'm going to measure saturated groundwater beneath that. All right. This is a constant area of debate between folks in my lab, whether or not these really transient soil wet ups correspond with a bedrock wet up beneath it. All right. And my modeling at least seems to indicate that you have to fill the bedrock up before you can fill the soil up. And so we really have a bottom up filling of a watershed. All right, so this is the groundwater flux in the first layer of the bedrock, starting from the bottom of the slope to the top of the slope. I've output a line for each day for my 10-year simulation, and I've just stacked them. All right, so it's a way of looking at the variance and the average conditions during this transient movement, all right? Now, if you're a groundwater hydrologist, I think this figure is like a conceptual model or changer, all right? It shows two things that are really, really interesting. There is this persistent recharge zone on the upper third of the slope, roughly, all right? This recharge zone varies, it changes depending upon the season, but it's sort of a long-term constant recharge zone, all right? It moves up slope, it moves down slope, but it's really focused around 2/3 of the way up the slope. It's constant, all right? Then there's this middle section where there's hardly any variance at all. This is the zone where the groundwater is really just moving laterally all year long, all right? It's sort of the constant groundwater flux area. And then we get down to the bottom third of the slope and you see this massive amount of variance, big switches between huge recharge volumes. So these numbers down here, -3, that's a lot of recharge entering the mountain block at the toe of the slope over a very short time over spring runoff. And then large times of a lot of groundwater discharge to the soil. All right, so when I'm above this red line, it's groundwater discharge to the soil. All right, so this bottom third of the slope, long-term, the sort of long-term average state is that it's discharging water to the soil. All right, it's augmenting the soil water, but it's undergoing these huge changes from recharge, storing water in the bedrock, to releasing this water in the bedrock. So there's these transient groundwater flow. People are really interested in nested flow systems. And here what we're seeing is on the bedrock, or in the bedrock, we have ephemeral nested flow systems that are transiently storing and discharging a whole lot of water in the bottom third of the slope. And we have this sort of steady state, long-term, slow recharge of the bedrock on the upper third. All right, really, really interesting. If you were to read any groundwater paper on mountain block hydrology, they will just apply a constant recharge across that whole mountain block. Everybody does it, all right? And here I'm saying that is just on a sloping slab with soil covering it. You can really expect two different styles of recharge. Really transient dynamics and on the bottom third, and this long-term slow storage up on the upper third. So let's look at how much of the soil water is moving through the bedrock, all right? So as a sort of crude measure of that, I've taken all the water that's exiting my model, all right, as the total discharge out of the model. And this red line here is for each time or output of my model, I say divide the amount of soil water or groundwater recharge by the total amount of water leaving the model, all right? So when this number is 1, I have as much water going into groundwater recharge as is exiting the hill slope, all right? All right, so the red is groundwater recharge, and what I want you to see is that as, and time is marching on, the 10-year time simulation period is down here. At certain times during spring, essentially, there's as much water going down into the bedrock in recharge as there is exiting the whole slope, all right? So this is giving you an indication that at certain times of the year, there is as much water going into your groundwater system as there is leaving or becoming stream flow, all right? So the groundwater system is a huge, this is the storage time. This is when we're taking this pulse of water and we're really pouring as much as we can into storage, all right? As the summer goes on, we have less and less and less recharge occurring, all right? And it goes down to something like, 5% of the water exiting is now being recharged or entering the groundwater system. So this is sort of this red dashed line is the long-term average fraction of the hill slope discharge that is going in, is going into the bedrock, all right? And it's something like 30%, all right? So long-term average recharge is about 30% of the total discharge coming out of the hill slope. All right, the green line is now, let's just think about how much water is coming back out of the bedrock and into the soil and augmenting the soil zone, all right? So now this is flux from the bedrock to the soil, all right? And during spring, when recharge is very high, turns out that the groundwater system is contributing almost nothing to the soil zone, all right? The soil during spring, the majority of water should be coming from predominantly through the soil water, all right? But as time goes on, as the summer goes on, you see the fraction of the total discharge coming out of the model from the groundwater system go up to 40%, sometimes higher, sometimes up to 60% if it gets really dry, all right? So what does this mean? This means that the groundwater system is acting like this big buffer. You're pouring water in during the spring, all right? And during the spring, Kelsey is right. Rob is right. Most of the water is shooting through the soil zone, all right? But while that's happening, you're also pouring water into your groundwater system, all right? Then, once spring's done and we start to dry out, now your groundwater system is all loaded up and it starts pouring water back into the soil zone and augmenting the soil zone, all right? The sort of long-term average total amount of bedrock discharge into the soil or out of the model is about 25%, all right? So I like to think about resilience much like a financial portfolio, all right? And your soil zone is your high risk and high reward part of your portfolio, all right? You make a lot of money or you're gonna lose a lot of money, all right? Your groundwater is like your bonds, all right? It just sits there, it's slowly accumulating water, it's slowly accumulating money for you, and then in times when the stock market goes down, everybody runs to the bonds, all right? So that they keep a little money coming in, all right? So this is our resilience. The groundwater system is acting as this constant source of storage, and it is not insignificant, all right? It's 25%. And when it gets really dry, 60%. Up to 60% of the water coming out of the hill slope is coming from the bedrock system. All right, so I'm gonna switch gears real quick and just look at the stream flow chemistry, all right, and see whether that agrees with my model. So I've been in fantasy land, running computer models. Now let's go back, look at some field data. And the third tool that a watershed hydrologist has is looking at chemical fingerprints in the stream and looking for different kinds of water. Is that water coming from soil? Is it coming from bedrock? Are there chemical constituents that we can see that might be able to distinguish that? So I'm going to use two different techniques. The first is radon. Radon is only radon in water with no groundwater. Radon in equilibrium with the atmosphere, or sorry, water in equilibrium with the atmosphere has no radon in it at all. But groundwater is exposed to uranium and thorium decay, and it always has some radon in it. So radon is a really sensitive indicator of subsurface water discharge, right? And I calculate the amount of water coming in by modeling radon in the stream concentration or in the stream. Bottom line here is we can measure the radon in a stream and we can tell you how much groundwater must have been coming into the stream in order to give us that radon concentration. All right, we also use just the stream chemistry, and we came up with a new multi-component mixing model. Again, I'm not gonna belabor this, even though it's super cool, but the point is the longer water's underground, the more water-rock reactions occur and the more solutes you have. So groundwater generally has a different chemistry than soil water, and we try and use the chemistry we measure in the stream to back out how much groundwater came in and how much soil water came in. All right, so here, this is a result during the spring rising portion. And this is the total discharge, this top line. The bottom line is the total amount of subsurface discharge. And what the radon's telling me is that all of my stream gain over the rise of Cap Wallace, or over the length of Cap Wallace, is coming basically from subsurface discharge. All right, I have, even during spring snowmelt, I have no chemical signature of snowmelt water, actually. It's all going through the subsurface. My multi-component mixing model is basically showing me the same thing. You're going to see a lot of purple and red here. That is soil water. One is like super dilute soil water. I'm calling that pure soil water. And red is soil water mixed with some groundwater. All right. And what you see is that using my chemical mixing model, that all of the water, this is going downstream, all of the water we've added to Cap Wallace has come from some amount of soil, has basically come from soil water with some amount of groundwater mixed in. All right. Here's spring falling. So this is just right after peak water. Black here is a bit of snowmelt water. So again, radon's telling me that almost all the water that's entering the stream is coming from subsurface discharge. I can sort of back out the constant or the different sources of that using my stream chemistry. And up higher in the basin, I see some effect of direct snowmelt addition to Cap Wallace. But as I move down by the bottom of the basin, all the water has basically come from subsurface sources. All right. And half of it is from really shallow, dilute soil water, and the other half is basically from soil water that's more concentrated and has groundwater mixed into it. All right. Okay, finally, base flow is the same idea. Basically, all the water coming into Cap Wallace has come from subsurface, and it's about evenly split between dilute soil water, shallow soil water, and soil water with some groundwater in it. All right, so the chemistry is reflecting the same thing that tells me that, first of all, bedrock groundwater is a real thing, and it's an important thing, and it is causing or adding resilience to our system. All right. The bedrock groundwater is a dynamic system. All right. It is constantly changing throughout the year. All right. And it's changing much faster than I think most groundwater hydrologists would think. All right. The seasonal changes are big. The recharge locations are very particular and very different. So when I look at a hill slope now, I don't think of the whole thing as a recharge zone. So a mantra in groundwater is that the world is a recharge zone. All right. Really, when I look at a hill slope, the top third is a long-term recharge zone. The bottom third is an ephemeral, short-lived recharge zone. All right. There's this ephemerally nested, shallow flow system. All right. There's all kinds of chemical signatures that have really thrown the water world out, that this short, ephemeral, nested flow system explains. All right. Bedrock, it's important. It's about a third of the total hill slope discharge at one point moves through the bedrock, right? This is actually a number that's been reached in several other papers of bedrock sort of roles in groundwater or in stream water generation. So it's not the most, it's a third, but you could argue that it's some of the most important third because it comes out when you're the most water stressed. It offers the biggest buffering to long-term drought. All right. And finally, our chemistry and our field measurements are starting to corroborate this numerical modeling exercise and showing that the stream, at least in Cap Wallace, is mostly subsurface discharge. It's coming from a mixture of soil water and groundwater. All right, and that the subsurface water is the major player. All right, this is not just the Cap Wallace result. There's lots of other papers showing this. But the bottom line is that when we think about stream flow and stream flow generation in our uplands, the groundwater component should be thought of. Its role in preserving and enhancing or buffering stream flow generation during climatic fluctuations should not be underestimated. And how these dynamics are going to change as say snowmelt dynamics and or precipitation dynamics change is a really interesting thought, and sort of thinking about how this mountain block system is going to both absorb those changes and then long-term see climatic effects is very interesting. All right, so thanks for listening, and I would be happy to take any questions. I'm clapping for myself. Yes, sir.
So can we move to a funny kind of bedrock? And that would be the bedrock which is deposited away from the mountain. So in a fan or east of the Rockies or something like that, and then apply your model to that as well.
I mean, that's a great question. So that's starting to look at a bigger scale. That's a great idea. And yes, I want to do that. But the people who have done that so far, and that is something that has been done in the groundwater literature, is sort of look at these big regional aquifer systems that extend away from the mountains. But generally, they just treat the mountain as a sort of uniform area of recharge. And so what would be very interesting to do is to think about how these topographic effects and these very location-dependent recharge would change our idea of how those aquifers are recharged. I think it's a great idea. Should be done. Yeah.
One more question. Similar path, but I guess more generally, how transferable do you think these ideas are? You can work isolator simulation conservation on this study, but what are the scaling properties? Where do you think they break down? For example, simplify to extending your whole slope to 500 meters. The critical scales at which it starts to break down?
I think that is a really good question, and actually a question that I'm trying to work on now. But I think there are lots of scaling issues. And I think the ability to transfer results like this on shorter length scales to larger length scales is a big question, and one that I'm not sure I can completely answer here. What I can tell you is that I have done work previously in large river systems, and this is sort of an excursion for me to work in these small systems. And in larger river systems, I tend to find this 25, 15 to 30% number of regional deep groundwater. It's just keeps popping up again and again. And there's been really large scale modeling exercises, like at the continental scale from folks at Colorado School of Mines, and they find this like 15% to 30% number as well. So I think there's some theoretical or some empirical evidence that it does scale, but I don't know that I can say that my results make that jump. You, and then Stephanie, and then you back. Yeah.
How much do you think that the buffering effect is affected by surface freezing and thawing? And as our climate begins to change, do you see that affecting what you expect to be the buffering capacity?
I think the buffering effect is probably fairly strongly affected by the temperatures and the way that the snow comes off. Turns out that the soil wets up, and at least in this drainage, once we sort of go isothermal, we don't often freeze a lot again. But I do think that those dynamics are really important. And I think that we need to understand how it's working right now in order to make those transfers to how changes in snowpack or changes in temperatures and freeze thaw would affect the buffering. I think the first step is to understand how it's working right now and then try to make predictions. I do think it's important. But I will say this, at the base of the snowpack, we tend to have temperatures really close to freezing, and we don't, as long as it's a deep snowpack, it's pretty thermally buffered. But processes within the snowpack itself get a lot more complicated, as I'm sure people here know. Yeah, Stephanie.
You thought a bit about tracers and helium for plus radon 222, which have really different timescales. And so you're working in an area where it's hard to find an appropriate tool in the tracer.
Yeah.
What's your thinking on where that can head with this work at the scale of Utrecht and these soil processes beyond the very short term versus bigger rivers?
Yeah, so I'm building a SF6 and CFC line right now. So if you don't know, SF6 and CFCs are refrigerants, and they've been released into the atmosphere by humans, and they serve as a tag of groundwater, and you can use them to age date the water the last time it was in contact with the atmosphere. I think CFCs and SF6 are, at this scale, will be a really, really useful tracer. And it's mostly just about getting the analytic capability to measure it in large quantities. And then adding a bunch of, the other key here is to add many tracers with different timescales. So radon, CFCs, stable isotopes, some longer lived ones like helium, and try and build the picture out. But for now, one line at a time. Yes, sir.
My question was probably along similar lines, but it's relative to things like radon. How does one, parameterize that to figure out how much radon is picked up? Because presumably that's parameterized, but then when you use that as a mixing model, it's only as good as the parameterization, right?
Yes, sir. So here's our equation, and yeah, there's a lot of parameters in there, and a lot of them have various amounts of uncertainty associated with them, but we basically take into account, subsurface inflow, evaporation, gas exchange, radioactive decay. Evaporation turns out to be not too hard to figure out. Gas exchange we can measure relatively well. Radioactive decay we know really well. Hyporheic exchange, well, if Jeff Poole was here, you would know that that's hard to measure. And then, but the big one is, in order to calculate subsurface inflow, I need to know the concentration of my groundwater coming in. That's the C sub I here. And this is the one that's really, really hard to get at. You have to measure it in the groundwater. And we've done that here, but there is uncertainty associated with it. So you got to understand how much uncertainty there is when you make your prediction, saying, well, I would never say there's exactly this much water coming in, right? I have to consider those uncertainties when I do that.
I guess that was more my question, is like, what does the error envelope look like when you propagate that out, rather than using that to verify the model? It seems like a good approach. I'm just wondering on, how much of that, in terms of
I mean, not to get too far into the weeds, but we've done some error analyses, and the error is probably on the order of 30 to 40%. It depends on how well you characterize the groundwater system. Here we've got it pretty well characterized, but in many places we don't. Yeah.
In the
flood model is also, what were the boundary conditions?
No flow.
That was forcing some of the water.
Yeah, it is. However, that there is some physical plausibility to that. So generally, beneath a stream, there's a groundwater divide. And so groundwater generally tends to upwell at a stream because there's a groundwater divide. So that it's not completely implausible to have one there. I have done some other models where this is like a seepage boundary condition. It changes things a bit, but it doesn't change the major parts of the story. And the reason why is because the soil has much higher hydraulic conductivity. So the water's naturally going to want to move towards that higher hydraulic conductivity conduit. So that in itself drives the upwelling, not just the boundary condition. Yes, sir.
I think this is a scale question again.
Uh-huh.
The heterogeneity of, you've dealt with a pretty homogeneous system.
Yeah. Uh-huh.
If you were to come into Southwest Montana, you have Madison,
Oh yeah.
Cretaceous and all
Yeah.
that. Does that blow this out of the water, or is it?
Okay, so there's a couple answers to that. Is first of all, yeah, heterogeneity is a real hassle, and then when you're in fractured bedrock, major problem. So what fractured heterogeneity will do is mess with the particular location of, say, a recharge zone, discharge zone. You have a certain fracture orientation or something like that. It doesn't necessarily take away, because I've parameterized this with sort of fracture characteristics from our particular block, then the main sort of average results are probably pretty applicable. And I've changed that, so I didn't have time in this talk, but I've looked at, we used fracture network properties from the belt on this one, but the model in my last slide is from a fractured granite, which is in a watershed directly adjacent. And that has completely different fracture network properties. And you see a big change. And so it is really important. And the fracture properties are really important. So this is just the first sort of, well, on a hill slope of one rock type, you know, but you're right, geology changes and it matters for sure. The idea would be that we would understand how geology would change these particular results so that you could move from one geology to another and understand the basic effects, right?
Well, I think we probably need to vacate the room at some point. So thanks again.
Thanks for the questions, guys. They were great.